Okay, so dynamic equilibrium, and that's just whenever the two phase change, kind of phase changes. The solid is going to ion, aqueous ion is going back to solid at the same rate, so the rate forward equals the rate reverse. Which of these is least soluble according to the Ksp value? That meant that you probably had to have this table in front of you, sorry. You probably couldn't answer number 2, unless you had it on your paper because you wrote it out. So what was the Ksp value for calcium fluoride? Oh, just the Ksp value, just straight up the value. It was 3.4 times 10 to the negative 11. The second one was 1.1 times 10 to the negative 12, and 2.3 times 10 to the negative 9, okay? So if you're seeing these values, ignore the fact that we do have different numbers of ions here. So this one's 3 ions, this one's 2 ions, and this one's 3 ions, 2 ions. Ignore that for a second. If you're just looking at Ksp values, which of these is the least soluble? Right, so with the least soluble, means that you have so few products that the K value itself is very low because the numerator is so low, it means the K value is very low. It's just a normal K expression. It's just, in this case, talking about specifically precipitates going into ionic solution, or going to aqueous solution. So that means that you have very little of these 2 ions forming. And obviously it's a solid, the silver heavy metals, it's commonly going to be really small. What else was I going to tell you there? I was going to tell you something else. I'll tell you in a second. Okay. Relative solubility usually means like relative to something else. So I just reviewed this in biology. Relative age of fossils, if you have a low layer and a high layer, relatively who's older? Low layer, because the last layer formed last, so it's the youngest. So you don't put a number on it per se, but you just say it's more soluble or less soluble. So relative solubility can only be compared if you want to just look at numbers and say this one's more soluble or less soluble, only if you have the same number of ions, okay? So you have the same ion-to-ion ratio. So if you're comparing something with 3 ions formed versus 2 ions formed, it's like comparing apples and oranges. You cannot compare their Ksp, their solubility values, because they're just totally different numbers, and it significantly affects the Ksp value. Solubility changes with temperature. Good. Temperatures, usually warmer temperatures usually are going to be more soluble, or make more ions dissolve in solution. Not all the time. It depends on if it's an exothermic dissolving process or an endothermic dissolving process. So if you add temperature and it's exothermic, which way does the reaction shift? To the left, to the reaction. So if it's exothermic and you add temperature, you heat it up, it's shifting away from the exothermic rate. Exothermic is heat on this side, so it's going to shift back that way. So it actually can affect the ability of something to dissolve if you change the temperature. What does solubility refer to?
3 grams.
Okay,
greater than 3 grams dissolving in 3 milliliters of water.
Okay, that's like saying something is soluble or insoluble. I was just going to say the amount of moles of solute in 100 grams of water. Things actually like on a solubility graph, it's moles. Or it might be grams of solute over 100 grams of water, but it's referring to a specific amount and a specific amount of water. So I'm good with that too. What are the conditions of the solution when Q does not equal K? So Q and K were at equilibrium, right? Yes. What does that mean about the solution? Right, it's saturated. So what are the 2 other conditions that would apply?
Unsaturated and supersaturated.
All right, so unsaturated means you can continually add more of a particular salt to the solution, and it's going to keep on dissolving, no problem. So unsaturated, if it's unsaturated, you can continually get more and more and more dissolved. Does that mean Q is less than K or greater than K? Right, Q is less than K. Because if Q is less than K, that means you need to put more product in there to get it up to meet K. Well, what are the products here, solids or ions? Normally, I don't know if you probably saw this on some of your examples throughout that little reading guide. It was solid yields to ions. You know, if of course I could put a specific example up there. But if you wanted to make Q equal to K, you have to you have to increase the products. You have to increase the ion count. So you'd have to let more and more dissolve. So that's why that satisfies that. And then the other one will be supersaturated. And then Q would be too large. You have too many ions in solution, so you would need to allow some to precipitate out before you could actually come back to equilibrium. All right, what is the common ion effect? Yeah, new words.
Solubility decreases around common ions.
All right, so solubility decreases when in the presence of a common ion. Okay, and we're going to hit that a little harder. That's kind of like just basically definition right now. How does pH play a role? Anybody have any idea?
It can affect the solubility.
Right, just like temperature can affect the solubility, pH can affect the solubility. So it can either increase the solubility or decrease the solubility depending on the situation. We're going to kind of do some situation-based practice here in a second. And then the last one is kind of weird. It talks about that selective precipitation, which is like kind of a qualitative analysis method. If you go to chemistry in college and you go to qualitative analysis, it's pretty wicked. Just saying. So it deals with stuff like this. Okay. Separating cadmium and nickel ions require, and this was like one of the last questions on the actual reading guide itself. Separating cadmium and nickel ions require precipitation with sulfur. Use the Ksp values to determine which ion will precipitate first. As an aqueous solution of sulfide, ions added to a portion of the sample that still contains these ions, which precipitates first. So on that one, you had available to you a huge chart of all the KSPs. Gotta find it. It was pretty much asking, so if you have cadmium and nickel in the ion form and you add sulfide, what's going to happen to both of those eventually? Cadmium sulfide will form and nickel sulfide will form. And I knew this is nickel 2, it doesn't state it, but it's nickel 2 sulfide. So pretty much what it wants you to do, and these are, can I compare these? Can I do relative solubilities for these? Are they comparable? Are they apples to apples here?
Yes.
Right. Why? Because they both do what? Both what? How many ions do they form?
2.
Right. So you go to cadmium and 2+ and do your little thing here for it again. Oh, well darn. Got me all excited there for nothing. Okay. So cadmium 2+ sulfide, and then the same thing down here, nickel 2+ and sulfide. All right, so you can definitely compare their KSP values because they're both relatively the same. So when I looked up those values, I found the KSP for cadmium was like 8 times 10 to the negative 27, and the KSP for nickel was 3 times 10 to the negative 19. So who's more relatively soluble? Nickel, because it's got a larger K value. So that's 10 to the negative 27, so that's like 26 zeros and then an 8, and then you got 18 zeros and then a 3. So this one's actually a larger value, so it would be relatively more soluble. So who would precipitate first? So if it's more soluble, it's going to keep staying in solution, right? So it's going to precipitate first, which would mean it's less soluble, would be the cadmium, right? So we're going to talk about that in more detail, but I kind of am really happy with some of the feedback. So I think you guys, when you're reading it, I think maybe you're familiar with the solubility and how it kind of connects to equilibrium. Now we're really going to intertwine the two. But before we do that, I'm going to pull back up to the KSP value. You guys take a minute to let some of this stuff sink in. Make me a snowflake, not a snowman. Or no, let's make a snowflake. I don't know. I can try to. Do you want to make a snowflake? Thank you. It's not a question. It's a.
Hey, wait, Miss Emma.
Hey, wait.
Like on my phone, can I pull it up?
Yeah. I've lost the mouse. Where is the mouse? I've lost the mouse. I don't know where the mouse is. It's not up here.
Wait, don't you make a triangle? I don't know. Oh, there it is.
Where's it at?
Triangle. You make a square.
Aha, I see it. Okay. I don't know where it was.
Chinese paper cups. You're holding it toward you.
All right, so choose your favorite. I have no idea how to do this either. I'm just gonna make like, yeah, I'll figure it
I'm
out.
gonna do something like
It's not very often you get to do this, so enjoy your time with arts and crafts.
Okay.
I'm talking about AP chemistry. It's a specific trait. I did not realize this. I'm just gonna go crazy and like. This is gonna hate Jesus.
Like she's like over here like this huge thing it's in there and we're over here like
I've got like oh look, I got some more. Come grab some other scissors if you want.
what?
I don't have to actually make it work. You need like a better picture, really.
You just be
I'm gonna when you talk. Monday, I'm still here today. Tomorrow I have a meeting until about 3:30. Every day.
And then once you do this,
I can help you. I can make video stuff too. It's just this thing doesn't sometimes doesn't say. It's just out of nowhere. So I'm going to yeah, I'm gonna
yeah, she either wants to attend masquerade ball or a shack for she wants to be a maniac and throw a masquerade ball or live in a shack in the woods in Georgia. Look at this Emma over here.
I gotta do something cool. Alright.
Wait, how do you hold this? What are you?
Do you want better scissors?
What are you? How do you? I can't be a student degree. I can't.
Those are bigger. I can't say they're better.
Okay.
I don't have adult scissors.
Yeah, I need big girl scissors. My fingers are like too fat for this.
Yeah, do you have big person scissors?
Medium person. Oh, there's some over here. Look at these big peaceful scissors right here. Scissors everywhere.
Oh, I like this one.
Hey, wait, can I hand you the other side? You're gonna cry.
Please.
Please, no, Daniel cry. You made a wrong cut. No, Daniel, don't cry. You know Elf was on that. I know, I watched it.
The Snapchat story?
Yes.
I was like, really? So I don't care at me.
What is with you guys?
You don't share for something on your paper.
I don't know. What is it?
Alright, so I'm done. So about you guys? We have a Ksp.
I'm still.
What the heck? That's not a snowflake.
It is a snowflake. Every snowflake is unique.
A 100 square.
It is a cool snowflake. It's not mainstream like yours.
Don't come for me.
We're gonna fight.
Oh my gosh, it's so complex. If you don't finish now, you can finish at the end of class, but this is just a quick warm-up activity. I'm not saying it's going to be the whole class, because we have to do Ksp today sometime.
Oh my god.
He's trying to
I heard you guys call her that.
I need big person scissors.
Sharing is caring, people. Share the people.
But I don't want to share
Why is
screen.
it
I don't know.
I have Sharpies here. I don't know what color you want.
Look at my middle.
Huh?
Like a monster mouth.
Okay, that works. Thank you.
So we're just writing down the formula and then the
I'm gonna erase it. So like you just write down, I'm gonna do this one, don't steal mine. Aluminum hydroxide is mine, people.
Wait, I create. No one's doing the iron hydroxide. It's mine. I'm doing silver.
And then you're gonna write down the KSP value.
Silver acetate.
I'm sorry, the KSP expression.
You have glitter.
Not with me.
I called it first.
That makes me sad.
I called it in my head. That doesn't count.
Whatever.
It's hard to recall.
I called it before I was born.
You get to come back on a fun day. You get to come back on a fun day. Today.
Oh my god.
This day. Because there's arts and crafts for like the first 10 minutes of class, and then we hit the road running. That will be awesome and stuff, but
We don't have time.
unfortunately, AP Chem, we have to cover 2 semesters worth of material in a semester 0.75. So it's unlike other classes, which is like a semester and a semester, or a semester and a year, which would be awesome. Yeah. Yeah. All of them at once. Like that. So you're gonna get both.
I don't know how this is gonna. Okay. This is so bad.
Right? Like.
I wasn't gonna say anything.
Ow.
Oh, ow. I think
I'm lying. I'm lying.
No, it's okay. It's the truth. Look at my. It's so jagged because it's so thick. Oh, look at these edges. Working out my lungs.
Oh, you're right.
Yeah, I'm going intense today.
Literally, my sister wins like every time.
Oh my gosh, Daniel!
That's what I was calling. Okay, now I gotta put some
No,
right.
you keep Okay, so now yours is a little bit, tiny bit free.
It's cool. My own nails.
Consul's gonna be like,
Very cool.
I don't think so.
You fix it, yeah.
what's wrong?
It's looking a little. Yeah.
Like Avery was like,
You write the how it dissolves its expression. You write the products, and then you raise it to their. So like this is a coefficient of 1, so you raise it to the exponent of 1. This is a coefficient of 3, so I raise it to the exponent of 3. Over the reactants, however, this is solid, so it's irrelevant. So you don't put it over anything. So it's always KSP or K values are always products of reactants. But yeah, you ignore this. And so then I'm just gonna write the KSP value as well.
Whatever you feel most comfortable with.
4.62.
I would.
It says subscript SP. All right, Sharpies. Anybody else need a Sharpie?
Some more.
I've got all kinds.
Oh, the purple.
I've got pastels. I've got bold colors. I've got. I think I have neon in the back.
Okay, I'm gonna start writing any more Sharpies.
I don't know. I got fish clean.
I know. Sure.
Like my scissors are fine.
Looks like a train. It looks like a train. Like, I just have what do you think you want? Say it in English.
Oh yeah, it does look like a train.
Stop. It's mine so hard. What? Alright, Amazon?
Yeah. For the bottom, you can make a.
Okay, I'm going out for scraps.
Trim it off like that. I got it off the.
I can't do that.
I can't recycle
Teamwork.
scraps, so it's cool.
Let's see it, guys.
I was about to say.
I thought maybe that was the real deal.
Did you watch the other video?
Yes.
Oh!
Weird.
Oh! They found, like, the scientists came across a spider that's like
11 inches long and weighs up to half a
Oh
pound.
gosh.
I can smell the fermented milk.
Okay, you
I
ready?
was trying to.
Let's go, Sam.
I don't think it's a swastika.
Wait,
That's not what I was going for.
oh my god. Grant, let me see. Oh my god.
That's the great stuff like.
Tibetan Sanskrit, something.
Oh, great.
Okay, you're gonna finish whatever you can in the next minute, and then we have to start, and you can finish this later on. So, any more trash I can collect? We have the smallest paper winner over here, right here. Okay, yep. Smallest paper confetti. Yep.
Alright.
Let's see, you can cut the smallest.
Stuck together. Oh, well, those little cups made it even better.
Aren't you proud of your baby?
I'm such an artist. I mean, I copied the design online, but it's not the exact one.
Oh, sorry. All right, keep the shopping box for now.
Oh, great.
Like what wine, I would really be
Very.
I had a design in my head that didn't look anything like this.
Don't we all? It's so big.
Probably like literally everybody have like that. It smells like formaldehyde.
You can send me like sweet blue.
You write the actual things you got too. I'll put it back up there and hold it, okay? All right.
Creepy clown.
Make your final mark for now, and then we're gonna pick back up on it in a second, okay? So get ready, Freddies. I'll take the scissors back later. Just leave everything to us.
Thanks.
Is who. And then once I get my flask up there, I will put this up.
I need something.
Yes. Okay.
Okay, I'm ready.
This is like Jeopardy. Scissors down. Final answer.
Let's try.
Okay. So paper thing. All right. So this almost is almost exactly what was on. I think was on the reading guide because I typed up because I thought some of the phrases she used in the explanations were good. So I'm gonna let you guys write down what you need to, but I just pretty much want to give you some background on KSP, and then we're gonna do all the problems throughout. We're gonna pretty much. I asked for you guys to set up the KSP problems from the reading guide. I'm sure some of you guys were like, oh my gosh, what in the heck is this? So I tried to kind of kill two birds with one stone yet again by reviewing it and teaching you at the same time. Okay, so if you've read the questions and you set up something, then it should be familiar. If not, I'll be moving faster than you probably want me to. All right, so KSP does mean solubility product. We've already read the reading guide, so we know that the SP, the solubility product, is literally the product, which means multiplied, of the solubility of the ions, meaning the molarity of the ions. So it's all based on the fact that we formed a precipitate, and now we always know, yeah, 100% of that precipitate actually is solidifying and hitting the bottom of the test tube. It looks like a solid. So we normally assume 100% of it dissolves. 100% of it precipitates. However, there's always that tiny bit that does dissolve, and so that's what we're referring to, that tiny bit, which is reflected in a very, very, very tiny KSP value. So my favorite example to use is silver chloride, because we all know that silver chloride from honors chem forms a precipitate. And so that's usually based on a double replacement reaction between like silver nitrate and sodium chloride, so forth, makes silver chloride, okay? So we know it does that. So a lot of times you'll be given a question where you're actually given two reactants, and you have to think about the formation of the precipitate, and then you have to write the KSP for it. So I sometimes write out my BC for the double replacement, sometimes I don't. If I know what the precipitate is that I'm forming, I go straight to the precipitate, and then I write out the equilibria, or the dissolving of it. So I know that this was my precipitate that formed. So then from here, this is all useless at this point. This BC is useless. I take my precipitate, and I write it as a reactant, and then I show how the solubility equilibria exist. Because most of the time a KSP problem could care less about the actual BCE of the full reaction. It cares about just the solubility equilibria, just the precipitate going to the 2 ions or 3 ions or whatever it forms. So that's why a lot of times you'll write it out first as a BCE, and then you go, oh no, all I care about is this, and then the formation of the ions that it equilibrates to. All right, so that's called dissolution. So normally, when they're the first bit of solid forms, there are no ions that you've created right here in solution. So it needs to meet equilibrium. So some of them start just a little bit start to dissolve until you met your K or Ksp value. Okay. So the ions are going to increase until they become so plentiful in the solution they start to collide back again. So like in this case, the Ag plus and the Cl minus would start to collide again when they're in a saturated solution at this point, and then that would allow for more precipitate to form. So it is just a rate forward equals rate reverse. Rate of dissolving equals the rate of precipitation at equilibrium. What condition would this be for the solution? So this is at equilibrium here. You would say the solution was what? Saturated, right? Saturated. And then you can see the two equations here. These combine into the double-headed arrow equilibrium reaction. So a lot of this stuff is going to be in your reading that you guys saw. And sometimes they'll have you guys draw what the solubility or what the dissolution process looks like. And I'll make this little again, but I'm going to make it really big first. So you actually can see the ionic solid here. What is going to be kind of pulling off the negatively charged ions? What part of water? The hydrogen part, the positive side of water. What's going to be pulling off the positively side of a charged ion? Oxygen. So it's called the hydrations of water because water is literally pulling it apart through its hydrogen bonding or ion dipole moments that it's forming with the ionic solid. So sometimes they'll kind of have you diagram it. It's something that you're somewhat familiar with. So, alrighty. So this is all stuff that you can read again too from your reading guide. All right. So the dynamic equilibrium is what we are concerned about. That's the saturated solution. Okay. So we already talked about this at the point where no more solid can dissolve. That would be considered saturated because it's literally saturated with what? What would you say it's referring to? The water is a solution saturated with ions, right? The ions of interest, right? So yeah, be proud. It's good. If we're wrong, we're wrong. Whatever, who cares? So no more solid can dissolve because it's saturated with ions. So you can't push any farther to the right on that equilibrium because if you do, you would surpass K. And K you cannot surpass because you're trying to get to equilibrium. It doesn't go past K and like, oh, back out, we gotta go back, let's precipitate some. So it's dynamic up until, it's going to continue dissolving up until the K value is met. And so then we start, okay, well, now we know the ions present, now we know the values of the ions or the molarities of them present, we can call that the Ksp constant or the solubility product constant because it's literally the product of two ions and the soluble ions. In a lot of times they'll ask you they'll say like, oh, this is the Ksp at 25 degrees C. Generally, they're not going to be changing if the temperatures on you, like try to mix you up. It's not going to be a trick question. They just put the temperature because it's a standard, like it's something that we always raise. Like we try to define it at a specific temperature. A lot of times you never use that temperature, so don't get crazy with trying to say, oh, I've got this temperature, I've got to use it. So don't get too distracted by the fact that the temperature is going to be given. The other word that I don't believe was in your reading guide was we have another name for Q for this particular type of equilibrium. Q was originally called what? Reaction quotient. Good. Okay, so a lot of you guys remember that. Originally it's just called the reaction quotient. We compare Q and K. But for some reason we have to call the Ksp just a little bit different. It's called the ion product constant because you're literally making the product of two ions in solution. So the whole time you've noticed that I've been ignoring the solid because the solids are irrelevant for Ksp because solids are irrelevant for all equilibria. And so ion product, if you have, if you're given initial concentrations of two ions, you can plug it into the Q, and sometimes it's labeled like Qi for ion product versus just reaction quotient. It's the same thing though. You just plug it in for your reactant, for your two products, product 1 and product 2, and you raise it to whatever their powers are. And if the Q is greater, then KSP, it'll do one thing, or less than it'll do something else. So that's just going to allow you to determine if you're going to be proceeding to the left or proceeding to the right. Because if you know you proceed to the, if you know that you proceed left, do you subtract from the product side or the reactant side?
Product.
Right, you subtract from the product side and you add to the reactant side. And of course, the opposite the other way. Okay, bored to tears, I see you. Okay. We just talked about this relative solubility. Like you can compare magnesium chloride and calcium chloride because they have the same number of ions that form, but you can't compare apples to oranges. You have to compare apples to apples. I think that we did that. Sometimes, like on my problem sets, instead of just saying solubility, I actually say molar solubility if I want you to get the molarity. So I just said keep these two terms straight. If I ask for molar solubility, I mean moles over liters, if that's what I'm asking for. If I'm asking for just general solubility, sometimes it'll, I'll try to indicate that those, because it's not very common to see it this way. I'll ask for grams per liter. So that's just me, and sometimes AP does that too. And all of this relates back to your solubility curves, which you've probably seen since you were in maybe 7th grade. I think so. So if you're on the line, that's your saturated solution. So at, at this temperature, 25 degrees C, you're going to be able to dissolve whatever that number is of some salt per 100 grams of water. If you're above the line, what would you call that? Supersaturated solution. If at this temperature you're under the line, it would be a unsaturated solution. Yeah. We'll catch you up. It means that the ions are going to come back together and be consumed as they form solid. So it's actually like you're consuming products to make reactants, because it's technically a reversible reaction. If you proceed left, proceed towards the reactants, you make reactant. If you proceed towards the right, you make product. And so you can't make something from nothing, so you have to use up something else. All right, this is the first question. If you printed this, I was going to text you on say print it, but if you don't want to print it, don't feel trees. You guys have seen these questions because you read through this. Let's go through these together. All right, so I'm going to try to tell you some of the tips and hints to this trade too. So copper 1 bromide has a measured solubility. Okay, so in this case, this is molar solubility. And you might want to write down your givens unless you have this information right in front of you, unless you print it for yourself. Okay, so given solubility 2.1 or 2.0 times 10 to the negative 4th molar. Calculate its KSP value. Generally, what I do for every single question, first thing I do is write down my givens. Second thing I do is write out the BCE. Third thing I do is write out the KSP expression. Fourth thing I do is going to vary. So it's going to vary based on what I'm looking for in the problem. So I'll write down what I'm looking for here. So my given I can see here is 2.0 times 10 to the negative 4th molar. This is literally saying that I have this molarity of copper 1 bromide, dissolved. But copper 1 bromide dissolves into two things, and that's what my next thing is here. So my copper 1 bromide, solid, is my precipitate, and it's going to dissolve into copper, I always put 2+ because it's so darn common. Okay, copper 1+ and bromine ion. What is the KSP for this? KSP expression. Concentration of copper times concentration of bromine, okay? And that value is what we need to find, right? I need to move this. I need some space. I try to not write my KSP expression right underneath my BCE because I usually need my BCE for something else, like an icebox. So, you know that initially, whenever you just first pop that solid into solution, how many ions are there? None, right. Initially, there's 0 of this and 0 of this. Okay, initially there's some amount of that, but who cares? It's solid. It's not relevant right now at all. So ice baby, and we have a specific amount of both of these products made. Well, I have no idea what that specific amount is. Right now, I don't. I'm just going to call it what? X, right? 1x because there's a 1, 1x because there's a 1. So add x, right? So you can now see that both of these are forming at the same rate. So you're going to have x amount of copper, x amount of bromide that have formed. If I put those into my expression, that would just be x squared, correct? Yeah? All right, I can't solve for x because I don't know the KSP value. We're supposed to find the Ksp value. So technically, using logic, that means I know X. If I don't know Ksp and I'm solving for it, it means I know X. I do know X, okay? The reason I know X is because it's telling me that this amount of copper 1 bromide is dissolving. Since this dissolves in a 1:1:1 ratio, whatever number I was given here for the copper 1 bromide, it's exactly the same here. So when it gives you solubility, I always think it has given me X. Okay? Anytime they give me a solubility, they have given me X. However, the value can change. So like if I was dissolving to 2 bromides, then I would have 2X here, and that would be me multiplying X by 2. But in this case, I'm not, so I'm just going to stick with they have given me X. All right, so if they've given me X, then X squared is just 2.0 times 10 to the negative 4th molar squared, which is, no calculator, 4.0 times 10 to the 4, negative 8. Yeah, because so 2 squared is 4, and then whenever you have exponents and you multiply them together, you add them, right? So that'll be like 10 to the negative 4th times 10 to the negative 4th would be negative 4th plus negative 4th is negative 8. Review of algebra 2. All right, so Ksp is this. Cool. All right, so I'm just going to keep walking us through these because I think that, I mean, if you have it and you're familiar, let's not try too many. Let's just do what we've done. All right, second example they gave you was not actually, it was like right above exercise 3, but I'm going to show you the difference between molar solubility and just general solubility. So the Ksp value for calcium carbonate is 3.8 times 10 to the negative 9. That's your given. Calculate the solubility. Okay, so now it's asking in this case, what's the solubility for molar solubility, which is what A is asking for, and then it's going to ask for grams per liter solubility, which is what B is asking for. So I've written my Ksp value. What's my BC? And carbonate, okay? And then those would be inside of your Ksp expression. So calcium 2 plus times carbonate. So far these have all been 1:1:1 ratios. What was I going to do this for? Oh, so I generally go straight to equilibrium instead of writing ICE all the time, because if I start with no product, I'm always going to have a 0. I'm always going to have a 0 as my I. I know my change is going to be plus some number of x's, and I go straight to equilibrium. So I just go straight to equilibrium off the bat. So how many x's have formed here? 1 and 1. Good. So I know that this reaction yields a Ksp expression of x squared now, because I'm just plugging in my x's here and here. So then all I need to do is solve for x. And what did I tell you x just generally meant? Solubility of, in this case, the calcium carbonate. But it just so happens that the solubility of the calcium carbonate is going to be equal due to the 1:1 ratio of this and this. So they're interchangeable. This x is equivalent to this solubility, and vice versa. So once I solve for x, yeah, what's the square root of that? I can look it up for you too. X is equal to 6.16 times 10 to the negative 5th molar. So that is the molar solubility of what? What chemical compound here? Technically everything, but what is it asking for? Calcium carbonate. And that's important because when we go molar mass later, you got to know what the heck you're actually talking about here. So this is the molar solubility of calcium carbonate. So that's the answer to A. And then your job is to take molar solubility to grams per liter, which is pretty easy. You got moles per liter. How do you get to grams per liter? All right, so you use molar mass in somewhere form. So times 10 to the negative 5th moles of calcium carbonate per liter solution. And then to get to grams, you just need to put moles on the bottom, grams on top. So that is 100 grams calcium carbonate per 1 mole of calcium carbonate. So that is 6.16 times 10 to the negative 3 grams per liter. And that is the just general solubility or grams per liter solubility. So far, so good? Okay. I'll give you guys a second there.
So that's the negative 3.
Yeah, it's to the negative third. All right, so next one is copper 2 iodate. Ksp value is given. Calculate the solubility. So what am I solving for? Also known as X. Okay, so I'm solving for X. I usually, if I see that, I'm just going to put that up there because I know that I will forget later on. So copper 2 iodate equilibrates to copper 2 and what? 2 iodates, right. That's one thing some people sometimes miss because they forget to see the 2 subscript there. So the Ksp expression is copper 2 plus times iodate squared. Tell me if I'm going too fast because a lot of this general stuff I go through really fast because, I mean, I think you know how to write Ksp or K expressions. That's the way I'm feeling. That's equal to 1.4 times 10 to the negative 7. So, since I've got my BCE, I know how many x's of each of these are forming, which is what? X and, right, 2x. So then in my concentrations, I would be saying, okay, copper 2 is just x, but iodate is 2x, right, squared. Simplify that. 4x cubed, right, because 2 squared is 4, and then x squared times x, so you add their exponents, so that's 4x cubed, is equal to 1.4 times 10 to the negative 7. Divide by 4 and cube root that thing. I got you here on the answer. Do what?
Why did you cube, or not cube, square, 2?
Because of the 2 coefficient that gets transferred to a 2 as my exponent in my K expression. And so I still do it down here too when I plug in my X values. So like, since I made 2 iodates here, my K expression requires me to take my coefficients and make those exponents, right? And so then I had to take my 2x that I made right here, and I plug it in, but it's still squared. It's just because I always write my expression first because that's when people, if you guys try to skip the expression, sometimes people forget to actually put the exponent. So I really try to enforce that you should write it first. Yes. Because it doesn't matter, those are mathematically unrelated. So you're going to make double the amount of that ion. That's just related to its concentration. Its Ksp value is related to its value of equilibrium as to where it lies towards products or towards reactants. They're 2 totally different concepts.
Why are you on this?
Because I did have 4x cubed, and I have it equal to my Ksp value. And so I have to divide by 4 on both sides to isolate the x. Thank you. Okay, so x value is, does anybody get it? I mean, I told you I'd do it, but I'm slow sometimes. 3.27 times 10 to the negative 3 molars what x is. And, you know, sig fig's 3.3. I like to just write out the whole thing sometimes. So that is the solubility of the copper 2 iodate. Is this becoming a little bit better? Okay, so the first couple of examples are fairly similar. Now the next one is interesting because you're reading and you see that you've got common ions here. So in the reading before, I was trying to talk about the common ion effect a little bit, but you're given the job of calculating the solubility of calcium fluoride. They give you the Ksp, but then it says in is another solution. So we've got another factor we have to consider, and I'll show you how we incorporate that here. So first step is, for me, I'm just going to write out the solubility, BC. So calcium fluoride equilibrates to calcium 2 plus and 2 fluoride ions. So that's our solid, that's our aqueous, and that's our aqueous. You don't have to put the states. What is our Ksp expression? Loud and proud, people.
Calcium 2 plus.
Calcium 2 plus and fluoride squared. Good. So if that's our, and Ksp equals in this case 4.0 times 10 to the negative 11. When they ask for calculating solubility of this solid calcium chloride, what are we solving for yet again? Right, we're solving for X. That's our question. However, X is affected by the presence of this other solution. So instead of the solution being just water, we actually have a solution of two things. We have a solution of sodium ion and fluoride ion. If you have a 0.025 molar solution of that, what is the molarity of each of these ions? Say again?
0.0125.
It's I'm sorry, 0.0. Oh, no. You don't break it in half. I see what you did. I thought you guys just said it wrong. No, you don't split the molarity of it in half because you're still making a 1-to-1-to-1 molar solution, right? So however many moles of sodium fluoride you have, this is not equilibrium because this is 100% soluble. You're going to make exactly the same number of moles. So if you had 1 mole of this, you're going to make 1 mole of this and 1 mole of this, right? So if you make 1 mole of this and it's still in the same volume of solution, the molarity is actually ending up the same as what the initial was. So what is the value of each of these then?
0.025.
Yeah, right. 0.025 molar and 0.025 molar, right? This one's important because it's literally in the Ksp expression. The sodium one, who cares? It's not involved with the equilibria, so we ignore it. So since you have this already, you must include this as the actual value of the fluoride ion. So if you said sodium fluoride ion is 0.025, then that's what you're popping in the box, in the concentration. You still square it, okay? So calcium we're going to put in a second. This is 0.025 molar squared. It still equals, because it's still going to come to equilibrium, 4.0 times 10 to the negative 11. Now your job is to literally solve for X, the X that we're going to be indicating up here. Normally, I would be writing these X's down first, but I didn't want to confuse you. So this one's going to be making 1X. Technically, this one makes 2 X's, but we really don't care because I can tell you right now, if I have an increased concentration of fluoride, which way is this definitely going to be shifting, left or right? Left or right for you guys? Right. If I have an increased concentration due to Le Chatelier's principle, increasing products would technically shift left towards the solid here. And if I actually calculated the true fluoride without being in this other solution, it would be higher than what we're getting ready to calculate. Anyway, I'm ignoring this 2X because I don't want you to accidentally multiply this by 2 or something. Okay, so this is just X, and I want you to solve for X. So we just take 0.025 squared, divide this by that, and then solve for X. You guys are math geniuses. That is 6.4 times 10 to the negative 8. Yeah. And this is molar. When you solve for X, please put a unit on it. When you put K's in there, no problem, no units, no problem, no issues. But for X's or for whatever you're solving for molarity, put molarity on it. All right, so this number is lower than what it would be if it wasn't in that sodium chloride solution. How are we on that one? Yay, nay? Okay. All right, okay, so this is the precipitation determination as if you're going to be shifting left or shifting right. We have talked about some of this, but if you want to write down anything, by all means, do it. I'll let you guys get a second to read that first. So you always have to compare Q and K anytime the question says, will the precipitate form? Will more ions dissolve? Will more solid form? Any kind of phrase like that, you're probably going to be given initial quantities for 2 reactants, aka 2 ions, and then you're going to go, okay, stop here. I've got to say, what's Q? And then you compare it to a K value that would be given to you as well. So that's kind of like a key phrase and go, okay, I've got to calculate Q. So generally, just as a verbalization of what these values mean, because this is very quantitative to say Q is less than K, blah, blah, blah. Sometimes you have to itemize or qualitatively discuss it as well. So if Q is less than K, well, Q is still I'm going to use my example from earlier, silver ion and chloride ion. If Q is too low, what is it telling you at the ion concentrations? You've got too many reactants and too little products, right? Well, the reactants kind of matter here. The reactants aren't involved at all in the Q, so I'm going to go with the other half of that. You've got too little products. Well, how do you make more products? Proceed right. You proceed right. And I don't like to say shift for the Q stuff because I like to use shift for Le Chatelier's principle, so I always say proceed here. Proceed right, and does that mean dissolve more or make more solid? Right, I need to dissolve more. I need to make more ions, okay? And that's because I have my equilibrium solid on the reactant side and ions on the product side. All right, so then if you had to discuss this one, what would you be saying about it? All right, so Q is too high. Okay, because
There's too many ions.
too many ions. Okay, so too many ions. So what are the ions going to start to do to each other? Right, the ions start to collide, and they stick together, which forms right solid precipitate. So ions collide, proceed right, and that would yield. I'm sorry, yeah, that other way.
Down.
Down. Proceed left, and so precipitate forms. All right, so the logic and the qualitative and quantitative should go together here. And then this one, equilibrium. Equilibrium, saturated solution. Forward equals reverse. Okay. And then this is something else you might read. It would say something like whatever it says here. Precipitation occurs until the Q equals K. So you always stop at equilibrium. You don't go past equilibrium. You always precipitate until equilibrium, or you make ions until equilibrium. So that's just a phrase that they use sometimes. And we already discussed that. All right, let's do one of these problems. And then usually the question, it'll say, will it precipitate? Will it precipitate? Will it form more solid? Will it form more ions? But it also will usually give you two totally different reactants. So like it might give you barium nitrate and sulfuric acid. It's going to give you two reactants in a problem like this. So it's going to have you see the different types of problems asked in here. Like in our problem right here, exercise 5. Okay, so these are a little bit more complicated, so I'm kind of walking through my process. You're given 750.0 milliliters of 4.00 times 10 to the negative third molar solution of cerium 3 nitrate. Cerium nitrate. Is that a transition metal? It's on the bottom. It's like
Yeah, like on the
strip.
bottom.
Also known as the inner transition metals. Oh yeah. All right, so I don't know the charge of that. I'm guessing it's a 3. I stated here. Okay, so we have cerium nitrate, cerium 3 nitrate, and then we have 300 milliliters of 2.00 times 10 to the negative 2 molar potassium iodate. All right, you know that these two things are going to react. I don't really care about the reaction. I care about what forms. What's probably going to form? Cerium 3 iodate, right? All right, and that's what we are concerned about. I could have you write out the BCE, but I don't want you to be confused by the fact that you got a BCE and then you got an equilibrium expression that's totally different than the BCE, because they are totally different. So I automatically go, oh great, I know what the precipitate is that they're asking for. And it, of course, it's usually going to give you the Ksp value for it as well. So it's no secret what they're looking for. So nitrates are all soluble, so it can't be that, because that would be potassium nitrate. So definitely the other one that it's asking about. So cerium iodate. Cerium 3 iodate is what they're looking for. All right, so I'm going to leave those there for just a second. So I'm going to use them. But you know your other stuff. You know you have to write out your Ksp expression. So cerium iodate equilibrates to cerium 3 plus and 3 iodates, because there's a subscript of 3. So that's going to be Ce 3 plus times iodate to the third. Good. Alright, and I like to just write it because I'm scared I'm going to forget to explain it sometime. When you go fast and furious, you do forget stuff. Alright, first step on this is, once you've assessed the situation, you kind of written down on your givens, is dilute the ions, okay? When you have 750 milliliters of something, and then you add another 300 milliliters to it, you've essentially diluted all these ions in this compound. Because you got it in more volume, right? Does that make sense? Alright, so we literally need to just dilute these by finding the total moles of said cerium divided by the new volume. That's it. Moles over new volume. So how do I get moles from something like this? One of those, yeah. Multiply. Alright, so we convert this to liters and then multiply, right? So this is now 0.750 liters times this many moles per liter. And that is, didn't write it down, did the whole calculation in one step. Okay, so, I don't know what that is, guys. I'm just going to show you how I did it here. Give me some space, dog. Okay. So I took my liters times my molarity. My liters and liters cancel out, but I need to take that whole mole number divided by my new liters, which would be what? 1 liter, 0.050. Thank you, I heard you. I just picked it up slower than you said it. Okay, so this is the first ion concentration. This many moles, whatever that is, divided by new volume. That equals my cerium concentration, which is 2.87 times 10 to the negative 3 molar. Yeah. You guys see what I did there? I know I just messed my work up kind of weird like, but okay. You guys are smart kids. And is this less than the initial concentration of cerium nitrate? Yeah, I got 2.87 and 4.0. Definitely less, and that makes me feel good because I was just said I had to dilute it, so it definitely has to be less. All right, so then I'm gonna do the same thing, but for the second ion. Well, what ion do I care about here? Right, the iodate. So here's my second one. Take this 300 milliliters, convert it to liters. So 0.300 liters times 2.0 times 10 to the negative 2 moles per liter. Liters and liters cancel, so now I've got moles divided by same new volume. You don't get to change volumes if you're talking about something else. This is a new volume, and that gives me an iodate concentration to be 5.714 times 10 to the negative 3 molar. You can see so far I don't really care about sig figs at this point. Well, maybe I have, because I don't want to round too soon. So this number after the 7, I don't remember what it was, but I rounded a little bit here, but don't round too soon, if not your calculations will be a little bit off. Alright, so here's my new volume. Is it more diluted? Yeah, we got 10 to the negative 3 here, we got 10 to the negative 2 there, so definitely more diluted. Alright, so it makes me feel good too, because I told myself I was diluting. Now I have both cerium and iodate, plug, chug, chug, tell me what the, so far we have not even calculated, we don't have to calculate KSP because we're given KSP. What are we actually calculating? Q, thank you, I just said it. So you're calculating Q. KSP is given to you, but you know the Q setup is the same as the KSP setup. The expression is the same. So this is 2.87 times 10 to the negative 3 molar to the first power, and this is 5.714 times 10 to the negative 3 molar to the third power. When you plug in those initial concentrations that we've just kind of diluted and got to, then Q is equal to 5.33 times 10 to the negative 10. And you can't see it, so I'll write the KSP out. The KSP was 1.9 times 10 to the negative 10. Is Q greater or less than? They're both 10 to the negative 10, so that's not helpful. So which initial number is greater? Right. So this is larger. All right. So Q is greater than KSP. Right. It is supersaturated. What happens when it's supersaturated? Right. oh yeah, precipitate forms. But you have to have all of this evidence for your claim. Because, I mean, if you say precipitate forms yes or no, you got a 50-50 chance. It's pretty good. But if you don't have any justification for it, you get no credit. Which kind of sucks. But, you know, you're good people, and you'll show your work and stuff, so. We answer the question, yes. Yes, it will precipitate. Yes. Is that right?
Yep.
Okay.
Well,
I probably should get Okay, let's do another one of these. Okay. It goes, yes. Yeah, yeah. Alright, let's do another one. You guys set up. Oh, babies are in a room. I need your paper. I don't need. She needs this. She's just using
You what?
I should have texted you, but it's cool.
It's fine.
Sorry, KSP has like 4 or 5 different types of problems, and I have to kind of switch it just one of each. Where? Yeah, that's the negative one right here. Like they could have just put 0.1. Oh, you guys may not be able to proceed past. I want to share something with you on this one. So tell me when you get to the point where you've got your 2 new concentrations. I got you. There's my marker. I didn't show my work on calculating it. However, you guys know you're still doing molarity times volume divided by new volume total to get your new molarity. Magnesium 3.75 times 10 to the negative 3. Proceed leg. Thank you. And then fluoride 6.25 times 10 to the negative 2. For my couple people. Good. Okay, so just don't forget on these, when you're given 2 solutions, you're adding the solutions so the volumes are additive. So you have to account for that by adding the volumes and diluting that molarity, because it is a totally new molarity when they've added together. But both of these are initial molarities, okay? So both of these are initially present in the solution. The only reason I'm going to do this one slightly different is because, one, it doesn't say does a precipitate form, correct? It doesn't say does more ions form. It's actually for the concentrations. It wants the new equilibrium concentration. So if it wants the new equilibrium concentrations, we have to actually set up an icebox for real this time, okay? So what they've just given us are initial concentrations of magnesium and fluoride. So those are the the initial. And and this is one where we're going to have to talk about Q and K again in just a second, okay? So magnesium is 3.75 times 10 to the negative 3, and fluoride is 6.25 times 10 to the negative 2 molar. So your icebox is a little funky because you already have values in here. Is this going to make more ions or make more solid? Why do you say that? I don't know. How would I decide that? Find the Q. All right, so I need to find the Q to decide if I'm minusing, because I actually do have some amount of solid there. It's just, it's not included in the icebox because you're not given values for it. So this is, I don't know, don't care. But I do need to know if I'm adding to that side or if I'm subtracting from that side. So I need to compare my Q. So my my KSP/Q expression, KSP/Q expression is, it looks like I'm dividing. I don't mean that. Or Q expression is magnesium 2+ times fluoride squared. So I need to plug those values into that, and you guys will tell me what you think in a second. Alright, so Q is 1.465 times 10 to the negative 5. Is that greater or less than the KSP value given? KSP is 6.4 times 10 to the negative 9. Greater. Okay, so it's greater. So what happens? I need to make more that thing on the left, the reactant. So I need to make more solid. So I need to make more precipitate. So I need to proceed left. All right, so first step here was ions diluted. Second step, ice. Third step, on Q, to just determine if it's proceeding left or proceeding right. Now I need to finish up my icebox. What do? Subtract x and, right, subtract 2x of my 2 coefficient right here. So then I'm going to have at equilibrium 3.75 times 10 to the negative 3 minus x, 6.25 times 10 to the negative 2 minus 2x. You shall not neglect x, because if you neglect x, you can't solve for x, people. So you cannot neglect x here as much as you want to, because the KSP is very small. You're going to have relatively little. Alright, so you're going to plug that into the KSP expression. Solve for x. I would recommend using your solver. KSP is equal to 3.75 times 10 to the negative 3 minus x to the first. 6.25 times 10 to the negative 2 minus 2x. What? Squared, as you have over here. You can see squared right there. Equals whatever the KSP value was. Thank you. 6.4 times 10 to the negative 9. You can do quadratic. I know you guys love it. Or you can do your solver if you can work that beast. And you will get x to be, you guys need, if you need to practice your foiling out and your math, that's on you, okay? I am more than happy to help you after school, but I'm not going to do that right now. You'll get x in momento to be 3.74788 times 10 to the negative 3. That's not the final answer though. What was the question again? New concentration, so what would I need to do with that? Let that thing back in here and here. Yes, ma'am.
When you put in your solver, do you divide the 6.4 times 10 to negative minus 5?
I do this and I subtract that. Right, because it's not being, itself is not being multiplied by any other thing, so it's just going to be subtracting it, so you leave 0 over here.
So you just subtract that.
Yeah.
Okay, that's x. I put my solver and I got 3,750.
You forgot a number, a negative or something someplace. So when you plug it back in, you get magnesium.
I forgot negative.
Yeah.
That's what it was.
I do that all the time. Magnesium, when you do 3.75 times 10 to the negative 3 minus x, you get 2.12 times 10 to the negative 6 molar. and you get fluoride to be 5.50 times 10 to the negative 2 molar. Ksp in like an hour, people. Okay, if you are still working, still work. I'm gonna save. I think I have like one more quantitative. I think I'm gonna save that after this. I'll do this Ksp. I'll do that tomorrow. Michelle Lies, I'll do that tomorrow. Selective precipitation. I'll do it tomorrow. This is in your packet. Tell me if you find it. It should be. If I copied it, not, I'll have to leave it up and you guys can Yay. I'm going to see if I can eliminate some of these. I know you're going to do one. Three. Yeah, unfortunately, the only one I'm going to admit is number 2. I tried. Yeah, these 4 and 5 and 6 you absolutely have to, and you need to practice on the common ions. And those are warm up. Eliminate number 2. Sorry, that'll give you more. So you guys can do those. Those are for homework. If you want to finish making your snowflake, if you need a break, do that. And let me see if I can. Let me see if I want to wait on that. We are going to do a Ksp lab tomorrow. We're going to do the calcium hydroxide lab that you'll see in your packet. So that I need you just to read and make sure that you're qualified to start in about 5 minutes tomorrow and not have to read through the entire lab and go, oh, okay, 20 minutes later, let's start the lab. Because it is a titration, and you will have to kind of set up a titration. But some of you guys are super fast with it. You can go through that thing real fast. So I just want you to be prepared for the lab so you can start as soon as we can tomorrow. Okay? So on your snowflake, you were supposed to write your equilibrium expression, your equilibrium reaction, your Ksp value, and your equilibrium expression. Mm-hmm. Yeah, you guys can see those. I'm at number 2. That's all I can do for you right now. Q pens around the room.
No, I didn't tell you that.
You can get it back if you need to.